In problem 5.57, which is an inclined plane problem, you're given that a block is sliding up an incline of 22 degrees with initial velocity of 1.4 meters per second. The coefficient of friction is given, and the question is in the A part, how far will this block slide up the incline? Okay, so here's the incline, and here's the angle theta. Block is going up the incline, and it's given given the initial velocity. Let me put the block a little bit higher up so I can get all the forces on here where we can see them. Of course, I'm going to choose this as the x-axis, and this will be the y-axis. And this thing has an initial velocity up the incline. And of course, it starts here. It has a force of gravity. I'll go ahead and show the vertical axis here. And I'll extend it down here because this is the angle theta that the force of gravity makes with the y-axis. So there will be, this thing's traveling up the incline, so the force of friction will be down. There will be a normal force, Fn, and because the friction force and the friction force and the force of gravity are pulling down on this thing, it will have a negative acceleration, and I'm going to show that as acceleration in the x direction is down, and the acceleration in the y direction is equal to 0 because of the constraint of the on the incline. So I think we have everything that we need. Now I'm going to go ahead and erase this picture, but from this picture we can see what the if we rotate that axis, we can see what it takes to draw a free body diagram, which I'll draw in just a minute. Of course, this is a kinematics equation. They want to know how far we go up the incline, so we've got to be able to solve for x. And so I'm going to erase this and show the equivalent diagrams that we need to solve the problem. The first is the kinematics problem, in which we'll go up a distance up the incline of x, where we have an initial velocity v naught x, and we have a negative acceleration of a sub x. And I'm just showing the one-dimensional equivalent, so I don't have to take so much space showing the y-axis. Now this leads to, in the A part, I'm just going to work the A part first, the free body diagram that looks like this. Free body diagram, in which the force of friction is along the x-axis, and the force of gravity is at an angle theta with respect to the y-axis, the force of gravity. And then we have a normal force, Fn. So there's the free body diagram of this mass as it travels up the incline. Now the given is the initial velocity, coefficient of friction. This is the kinetic friction since it's sliding. Remember, the static friction will actually be larger than that. And then the angle is 22 degrees. In the A part are unknown. So let me denote this first as we're talking about the A part of the problem right now. Our unknown is x in this part of the problem. And then we need something to tie all this together to find out what x is. If we know the acceleration in the x, we can use that v squared equals v naught squared. And let's go ahead and make this in the x direction, because that's where the motion is taking place, plus 2 times the acceleration in the x times x. Of course, we need the Newton's laws. We know that the sum of the forces in the y is equal to 0, but the sum of the forces in the x must be equal to the mass of the block times acceleration in the x. So let's go. What we have to basically do is sum the forces, and we're going to need the friction force. So we might as well go ahead and get the friction worked out. The sum of the forces in the y direction would be the normal force. Sum of the forces in the y equals 0. So you have a plus normal force minus the y component of the force of gravity. That should be a subscript. And so the normal force will equal to Fg, and then the y component is Fg times the cosine of the angle, like that. So there's a normal force. And of course, the friction force would be equal to mu sub k times the normal force. So that's Fg cosine theta. So there's what our friction force will be equal to. Now let's sum our forces. Let's see if this takes a little bit. I think I have enough room here for this part. So if I just use this right here, there's a little bit of algebra involved here. So let's sum the forces in the x direction. And both the friction force is negative, and the x component of the force of gravity, and that must be equal, the sum of those two must be equal to the mass times acceleration in the x direction. Plugging in then the force of friction minus mu sub k force normal minus Fgx. Okay, the x component is Fg. It's supposed to, that doesn't look much like an N, does it? Okay, Fg times the sine of theta, and that equals m times a sub x. We can plug in the Fg for Fn. As a matter of fact, we already have it down here, so I'm going to go ahead and put Fg cosine theta. Like that. That's supposed to be a minus sign right there. Okay. So there we go. Of course, we can take make Fg mg. And so if you factor that out, this is minus mu cosine theta plus sine theta. Fg is mg. So if I divide out the m's, then I get g ax. Okay. So there's the value of ax. I should put it on the left-hand side, but I'm not going to take the time to do that. This is the value of A sub x. And if I take this value right here, and there should be a minus sign there, sorry. If I take that value right there and plug it into my original x equation over here, remembering that we're going to solve this for v sub x equals 0. If we do that, then x, if you solve an equation, x equals minus v naught x squared over 2ax, like that. And a sub x is going to be a negative number. So if you plug all this in here for a sub x, you'll be able to get what x is. I'll leave you with that right there, okay, to solve for that. Okay, so that's basically the a part of the problem. Okay, just all you have to do is take this a sub x and plug it in there, and you'll get what x is. Now let's look at the b part of the problem. In the b part of the problem, it wants to know, okay, if it goes all the way up there, will it turn around and accelerate it back down? And the answer to that comes from comparing the force that's trying to pull it down versus the force that's trying to resist it, okay? So what I'm going to do here, so I don't have to rewrite everything, is simply redraw my free body diagram. So this is the free body diagram for A. Okay, what you see right there is the free body diagram for A. Now I'm going to do the B problem. Okay, so in this space right here, I'm going to do the B problem. And what all you have to do in this case, if it's trying to slide down, is just reverse the force of friction. Okay, so the force of friction will be in this direction. And the answer to whether or not it will accelerate down in this case, and of course now we're talking about the B part of the problem. Okay, this is the B part of the problem, is whether f sub f, whether or not f sub f is greater than f sub g. Okay, so what you have to do is just compare the value of the force of friction. In this case, that's going to be equal to mu sub k fg cosine theta. Look at the value you get for that, and fgx, that's the component that's pulling it down, is fg sine theta. So if you evaluate those two, you should be able to see that ff is going to be greater than fg. And don't forget, when it stops, actually it's if you knew mu sub s, the static, that's actually going to be the force that's going to be holding it up, because if it gets up there and stops, that coefficient of friction actually gets larger. So if this is true, if this is bigger than this, then certainly it's going to stay up there because the static friction will be greater. Okay, well that's 5.57, both A and B.